Welcome to the Deep Dive. We're the show built to give you, well, the ultimate shortcut to professional expertise.
Mm.
And today, we are taking on a pretty serious mission, actually. It's a deep dive right into the engineering heart of high-performance AI infrastructure.
Yeah, we're talking the big stuff, the,
Yeah.
multi-million-dollar systems,
Hmm.
the ones training the world's really cutting-edge models.
Exactly. And crucially, how you keep them running, like, perfectly.
That's right. And for this deep dive, we're actually digging into the core operational knowledge. We've basically pulled it from an analysis of the NCP-AII certification.
Ah, the professional exam for AI infrastructure management.
Precisely. So this isn't just theory, right? This is the practical stuff, the knowledge that stops outages and really unlocks that peak performance in these super demanding production setups.
And we should probably stress the context here. This knowledge, it's really high stakes, high value stuff. I mean, passing that exam, it basically confirms you're competent to manage systems where, frankly, failure is incredibly expensive. It's, what, 2 hours long?
Yep, 120 minutes, around 70 questions, give or take.
Rigorous. It really separates the admins who can just, plug in the hardware from those who actually know how to optimize it, how to make it sing.
Our goal then is to kind of synthesize the key architecture and operational ideas, the ones that really govern performance and, crucially, stability.
Okay, so we're going to unpack, 5 mission-critical areas, things absolutely necessary for maximizing the speed and reliability of these modern AI clusters.
Exactly. Starting right where the work happens at the compute layer.
Okay, let's dig in. First, big architectural challenge, sharing resources.
Hmm.
So imagine you've got one of these monster GPUs, right? Super expensive, super powerful, like an NVIDIA H100.
The latest and greatest.
And you have maybe, 7, 8 different dev teams. They all need guaranteed access at the same time.
Yeah, and that's the kicker, guaranteed access. Plus, you need logical isolation. They can't step on each other's toes.
Right, total independence. And you need that promise, that guarantee that if one team kicks off some massive job, it won't just tank everyone else's performance.
This is the classic conflict, isn't it? Density versus isolation. Because if you just share things using software, you always risk interference.
So what's the architectural fix? The thing that stops that contention?
The solution here is multi-instance GPU, MIG for short.
MIG. Okay, so why MIG? Why is that the definitive choice here? Couldn't we maybe just use standard virtualization tools or something to manage who gets what?
But here's the key difference. What's fascinating about MIG is the physical guarantee. It's not just software pretending to isolate things.
Not just virtualization.
No, it's hardware-enforced slicing. It lets you physically partition that single GPU into multiple smaller, completely isolated instances.
Physically partition, okay.
And crucially, each of those instances gets its very own dedicated, physically segmented slice of everything. Compute cores, streaming multiprocessors, its own cache, its own memory controllers.
Huh. So if I'm getting this right, we're basically choosing hardware guarantees over maybe some software flexibility here.
Pretty much.
MIG guarantees that performance because, well, if Team A starts absolutely hammering their slice,
Yeah.
they literally cannot steal compute cycles or memory bandwidth from Team B's slice next door. It's impossible.
Exactly right. It ensures deterministic performance because that resource split happens right down at the silicon level.
Wow.
Think of it less like sharing a big open plan office and more like building a stack of completely separate dedicated condos inside one building.
Okay, good analogy.
And that hardware isolation, that's the absolute key for enterprise-level stability and performance predictability.
Okay, so MIG lets us carve up the compute power nicely. But, having perfectly portioned slices doesn't help much if the pipeline feeding those slices is choked.
Right. Compute is only part of the equation.
So now we got to shift from compute allocation to what's often the real performance killer in big AI clusters. Moving the data.
Data movement, yeah.
They're talking massive data sets, terabytes, petabytes sometimes, living on these big parallel file systems, and you need to get that data super fast from storage right into the GPU's memory for training or inference.
It's got to be lightning fast.
How do we get around that huge bottleneck, the one created by having to go through the host CPU and the system memory first?
Yeah, it's a common trap. You see, organizations spend fortunes on the latest GPUs, only to realize the data path, the way data gets to the GPU, is their weakest link.
So what's the tech? What optimization do we absolutely need to deploy and check?
The technology we need here is GPU direct storage. GDS.
GDS. Okay, another acronym. But what's the fundamental shift here? What does it change in the cluster's architecture?
It basically, well, it revolutionizes the data path. It
Hmm.
creates a direct express lane, if you will.
An express.
Yeah. Think of the normal way. The host CPU and system memory are like a really crowded security checkpoint and maybe the check-in desk at a big airport.
Okay, I can picture that. Slow.
Very. In the traditional path, all your data has to queue up there, get processed, copied around before it finally gets to board the GPU, the plane in our analogy.
Right.
GDS lets the data transfer directly from the storage device. Could be super fast, NVMe drives, could be a big parallel file system like Lustre or GPFS straight into the GPU memory.
Whoa, wait. It skips the CPU entirely.
Completely skips the CPU and the system DRAM.
That's huge.
It is. By bypassing them, you eliminate memory copies, you slash the I/O latency, and you just massively boost the throughput.
So if you've shelled out for that high-speed InfiniBand network we'll talk about later and the best GPUs,
Then GDS makes sure they aren't just sitting there twiddling their thumbs waiting for the host system to slowly ferry data back and forth.
got it. So it's absolutely essential for these modern, really data-heavy workloads.
Couldn't build a serious cluster without it today, really.
All right, let's switch gears a bit. Moving from optimization now into maintenance, diagnostics. You've built this amazing, complex infrastructure, GDS humming, MIG slicing, and then suddenly, performance tanks.
Yep, the dreaded slowdown.
Persistently, the monitoring dashboard is flashing red, everyone's complaining. What are the specific, definitive signs that point to a severe, probably permanent physical hardware fault in the GPU itself?
Right. The kind that means you need to actually replace the silicon.
Exactly. Not just, a simple driver glitch or a config error you can fix with a quick reboot or a command.
Yeah, this is a super critical distinction for anyone managing this stuff. You really don't want to waste, say, 3 days troubleshooting a driver issue.
Only to find the card was physically busted all along.
Exactly. So, based on professional analysis, the kind of stuff tested in that certification, there are basically 3 key indicators. When you see these together, it's like the GPU is screaming, "I'm broken." It strongly, strongly suggests real silicon failure.
Okay, lay them out for us. What are those signals that mean stop messing with software, start calling the hardware vendor?
Okay, first one. Look for non-recoverable ECC memory errors.
ECC error correcting code memory.
Right, most server-grade GPUs have it. If the GPU's own memory is throwing errors that its built-in correction mechanism cannot fix,
Oh,
that points to deep persistent corruption or an actual failure in the memory modules themselves. That's a serious physical defect, not something a driver fixes.
got it. Unfixable memory corruption.
Yeah.
Okay, what's number 2? What's the next piece of evidence we hunt for in the logs?
You look for persistent XID error codes.
XID errors.
Yeah, these are like the GPU's internal panic button codes. They're NVIDIA's internal fault indicators. Now, the key word here is persistent.
Meaning they don't go away.
Exactly. If you see those XID errors pop up and then they reappear, or they just stay there even after you do a standard system reset or even reload the driver, that's bad news. It signals a severe underlying hardware issue, or maybe a firmware failure that's rooted deep in the physical silicon or the card systems. You learn pretty quick that trying to fix persistent XIDs with software tweaks is like changing the oil on a car that's been totaled. It's not addressing the real problem.
Right. Okay, unfixable ECC, persistent XIDs. What's the third leg of this stool? You mentioned it focuses on the connection.
That's right. The third thing to look for is critical interconnect faults logged by the system. Specifically, look for a persistent PCIe bus error related to that GPU slot.
PCIe, the bus connecting the GPU to the motherboard.
Exactly. If the system is consistently struggling to talk reliably with the GPU over that physical bus connection, well, that combined with the other 2 symptoms, the ECC errors, the XIDs.
And it paints a pretty clear picture.
Undeniable proof, really. The GPU hardware itself, or maybe the physical slot connection on the motherboard, is compromised. Time to schedule that replacement.
Okay, let's zoom out now. Pull back from the individual node to the whole cluster level. We're talking about scaling AI, right? Across maybe dozens, even hundreds of nodes.
Yeah, the big distributed training runs.
This relies heavily on collective communication operations. That's where all the GPUs on all the different nodes have to talk to each other, simultaneously, and they need incredibly low latency to do it efficiently.
Absolutely critical. Slow communication kills scaling.
InfiniBand is usually the network backbone of choice for this. So Focusing on InfiniBand, what are the, say, 3 essential architectural and operational checks you need to perform to really maximize that internode communication performance and prevent those scaling
Right.
bottlenecks?
When you scale out, the network basically becomes the new bottleneck if you're not careful. It can become the limiting factor, even more than the GPUs sometimes.
So what do we check?
We focus on 3 critical infrastructure checks. First, and maybe the most fundamental, is the network topology design itself.
The layout. Why is the design more critical than just, say, making sure you have the fastest possible links?
Because a bad topology, like one with built-in blocking points, guarantees bottlenecks. No matter how fast your individual links are, you absolutely have to ensure your network design, typically something like a non-blocking fat tree architecture, eliminates those potential congestion points.
Right.
If your design forces too many communication paths to squeeze through the same few links,
Oversubscription.
exactly, you get oversubscription, you introduce unpredictable delays, and that just destroys the whole point of having all those GPUs working together in a coordinated way. So getting that non-blocking architecture right is step one, foundational.
Okay, makes sense. Structure first. We've got a good non-blocking design. What's the next operational check? Something we need to actively monitor on every node, every connection.
Speed verification. You can't just assume everything's running at top speed. You have to continuously confirm that all the components are negotiating and operating at the correct high speed.
Which components specifically?
The host channel adapters, the HCAs on the servers themselves, and all the ports on the InfiniBand switches they connect to. Are they all running at the speed they're supposed to? HDR, NDR, whatever your standard is.
And what happens if one isn't?
That's the problem. A single network card, maybe due to a bad cable, a dusty port, or a driver issue, negotiating down to a lower speed, they can cripple the collective communication performance for that whole section of the cluster. It drags everyone else down. So constant speed checks are vital.
Got it. Topology, speed verification. What's the third piece for InfiniBand optimization? Something about the paths data takes.
Exactly. It's about the efficiency of the routes themselves. So the third check is routing stability.
Routing stability, meaning.
You need to verify that the subnet manager, the SM, is running correctly and, crucially, that it has generated stable and highly optimized routing tables.
Okay, and the SM is the brain of the InfiniBand fabric, right? It figures out the paths.
Precisely. Those routing tables it creates dictate the exact path that communication packets take between any 2 nodes in the fabric. If those routes are suboptimal, maybe taking unnecessarily long hops, or if they're unstable and changing all the time,
You introduce latency.
bingo. You introduce latency, you add jitter, and that immediately sabotages the efficiency of those critical collective operations like all reduce, which rely on synchronized, low-latency communication. Stable, optimized routing is paramount.
All right, for our fifth and final critical concept today, let's bring it back to supporting the people actually using this infrastructure. The developers, the data scientists.
The end users, yeah.
They're typically running their deep learning workloads inside Docker containers these days, often using those official NVIDIA NGC images as a base.
Very common practice. Makes things reproducible, portable.
So when the container team is doing their thing, building and running their models inside containers, what are the core operational responsibilities you, managing the host system infrastructure, have to get right to keep everything stable and performing well?
Okay. So when you bring containers into the mix, you basically create this necessary handshake, this interface layer between the host operating system and the kind of abstract world inside the container.
Right. They need to talk to each other properly.
Exactly. And there are 3 key software components or aspects on the host system that the infrastructure team absolutely owns and needs to manage perfectly.
Okay. What's number 1? Probably the most obvious dependency.
Driver compatibility. This is rule number 1, always. The NVIDIA GPU driver installed on the host operating system must be consistently updated. And more importantly, it must be compatible with the specific CUDA toolkit version that the developers are actually using inside their containers.
Okay, wait. Compatible with what's inside the container.
Yes, that's the critical link.
So let's play that out. If a developer decides, hey, I'm going to update my Docker file to use the latest CUDA 12.1 toolkit, what immediate domino effect does that trigger for the infrastructure team managing the host?
It means the infrastructure team has to immediately verify if their current host driver supports CUDA 12.1 libraries. If not, they likely need to schedule and perform a driver update on the host machines.
And if there's a mismatch, if the host driver is too old for the CUDA version in the container,
You get runtime failures. often really obscure ones. The container basically can't properly talk to or utilize the physical GPU libraries that the host driver is supposed to expose. It's this constant synchronization effort needed between infrastructure and the development workflow.
Okay, driver compatibility is key. What's the bridge? What's the software that actually connects the container runtime, like Docker or containered, to the physical GPU hardware in those drivers?
That's the second core responsibility,
Mm.
ensuring the NVIDIA Container Toolkit is correctly installed and configured on the host.
NVIDIA Container Toolkit.
Yep. It used to be called NVIDIA Docker 2, now it's this toolkit. It's the absolutely crucial piece of software plumbing. It allows the container runtime environment to actually see, access, and properly utilize the GPU hardware and all its associated low-level libraries sitting on the host.
So without that toolkit configured right.
The container is essentially blind to the GPU. It might run, but it'll just use the CPU. No acceleration. The toolkit provides that necessary bridge.
Makes sense. Driver, toolkit.
Yeah.
What's the third area of responsibility? Something more about ongoing health.
Exactly. It's about long-term health and stability beyond just initial setup and compatibility. It's continuous system maintenance.
Which involves?
Oh, a couple things. It means actively monitoring the system logs, looking for those recurring errors we talked about earlier, things that might indicate degrading hardware before it fails completely.
Proactive monitoring.
Yes. And it also means making sure that all the necessary firmware updates get done. Not just the OS and drivers, but firmwares on the GPU card itself, the server's BIOS or UEFI, maybe the network adapter firmware too. Keeping everything up to date is crucial for stability.
So true stability isn't just about getting it working initially.
No, not at all. It's achieved through that constant vigilance, monitoring, patching, updating firmware. That's how you provide a truly stable platform for those containerized workloads long term.
And there we have it. 5 really foundational concepts, absolutely critical if you want to master managing high-performance AI cluster infrastructure. The listener to kind of chew on as you think about maybe your next cluster design or upgrade.
Yeah.
Let's say you've invested heavily and you have a beautifully optimized, non-blocking InfiniBand network. Super low latency, high bandwidth. But maybe you haven't fully implemented or optimized GPU direct storage yet.
Okay. Common scenario, actually.
Which potential failure or bottleneck poses the bigger immediate threat to your overall workload performance? Is it a potential hiccup in the network that governs how fast the GPUs can coordinate with each other? Or is it the restriction in the data path, governed by GDS, that dictates whether the GPUs even have enough data to work on efficiently in the first place?
It's a tough one. The network governs the coordination speed, but the data path governs the fuel supply, essentially.
Right. It highlights that constant trade-off, doesn't it? Balancing the need to maximize that internode communication bandwidth against ensuring efficient local data delivery to the nodes. Something to think about.